Hello everyone, thank you all for watching. My name's Stuart, and today I'm going to talk to you about making your shell scripts portable by writing them in Golang using a library called Scriptish. Okay, so what's all this about? November 2019, I did 2 workshops down in Cardiff at DevFest Cymru, and one of them was the first presentation I ever did on Scriptish. My library that I've written for creating portable shell scripts. It wasn't possible to film the presentation on the day. I always promised I would come back and film and upload a video for it. So that's what today's video is all about. Alright. So, what's all this about? Let me start by explaining why shell scripts in the first place. Hopefully you've written shell scripts before. But in case you haven't, they're just small pieces of text, little programs you execute that you can knock up really quickly to start automating things. Any experienced developer who uses UNIX or any Linux system will have a whole collection of shell scripts that they've written to make their lives easier. And we do this because it takes literally minutes to knock up a shell script. It saves us so much time to have these little tasks automated. But that's all well and good. But what happens if you want to bring these benefits to other people? What happens if other people in the team want to take advantage of the shell scripts you've written? Or if you work in a larger organization, your group, or the whole organization? You see, when it's just you, there's nothing to worry about. It's your script, written to work the way you think, running on your equipment. And when you want to share it with the team, hopefully you're all using pretty similar setups and pretty similar equipment. But there's still going to be a little bit of teething trouble because shell scripts at the end of the day, they're not written to be robust. They're written to be almost throwaway pieces of automation. But your team's probably A, got access to you, and B, quite happy interrupting you and asking you for help and advice. The further away you get, for example, with the once you're sharing it to the wider organization, distributing shell scripts starts to get to be a pain. There's less chance that they're using the same setup as you. They may be using different hardware, they may be using different operating systems in this day and age. They're almost certainly going to think in a different way and work in a different way. And they're going to run into problems with your shell script. They're also not as used to talking to you, chances are. So there's going to be a lot more barriers to them adopting your shell scripts. So much so that they'll probably just write their own instead. And if you want to distribute your shell scripts to the world, something I do with the Git flow extension for Git, at that point, you've got to sit down and you've got to start to make them robust. You've got to start to make the scripts work with setups you've never seen, different versions of dependencies you've never seen. And in the short term, what happens there is that you end up with a lot of backwards and throwing, a lot of issues being opened as people say, well, hang on a moment, it may work for you, but it doesn't work for me, and here's why. So sharing scripts with the outside world, it can be quite expensive. And we can't forget people running Windows. No matter how you feel about Microsoft, the fact is that today, most developers are back on Windows. The days of going to a conference and seeing the majority of the machines being MacBook Pros are already gone. Whether it's the cost of the hardware, the uncertainty coming up with Apple Silicon, and the problems people are going to have with the fact that their Docker containers are going to stop working, people are returning to Windows. And many, of course, never left. And Windows, by default, doesn't run Unix shell scripts. Even making shell scripts work between different versions of Unix isn't straightforward. Shell scripts aren't written to be portable, they're written to be quick and dirty. See, shell scripts that do anything useful are calling out to other commands on your machine. That's what they're doing. They're not entirely self-contained, so they've got dependencies. And those dependencies simply may not be there on the other platform. People may need to install them, or you may need to support alternatives because no one's ported that code to run on that platform. Even if the dependencies do exist, there's no guarantees they'll behave the same way. You can take something like sed, for example, which is commonly used for search and replace. If you want to use that on Linux and you want to use it on macOS, you have to detect the platform and code them up differently, because that's one example of things that behave differently. In the past, the tools on Linux that obtain your current IP address, for example, I've seen those be different on different versions of Linux, different Linux distributions. So that can be a pain. And if you've shared shell scripts with others, I'm sure you've had this pain. People coming back to you and saying, "Oh, what do I need?" You give them a list, they go away, they install everything and they come back and you've missed a few things. As far as I'm aware anyway, there's no automated tools to go and make that list for you. You have to go through the script and work out what's a dependency and document it. So portable scripts, not fun. And that's frustrating, because if we're giving someone a piece of software to use, especially something that's supposed to make their lives easier, we want them to feel like they're getting a present. The last thing we want to do is for it to be a dumpster fire. We don't want it to turn into drama and pain. So how do we solve that? Well, I think the answer to that is to change which language we're using. Instead of writing these little utilities in Bash, I think we should be writing them in Go. So why Go? What is it that Go gives us that shell scripts doesn't? First of all, we don't have any dependencies to worry about. A Go program compiles to a single self-contained binary. We can give everybody that binary, and as long as they're running the operating system it's compiled for, the binary will work. Your code may not work on every platform, that's a different problem, but at least there's nothing else to distribute. Bash has grown so much over the decades that I've been using it, and its predecessor, the Corn shell, but you still can't beat a programming language that's written for writing large-scale code. Golang, being originally aimed at systems programming, it's got a very powerful programming language, and it's got a very powerful standard library. And it's also got a growing ecosystem of third-party packages that you can pull in as well, third-party libraries that you can use to avoid having to write everything yourself. And another useful thing about Go is you can use the cross-compiler support and make your utilities compile for Linux, macOS, Microsoft Windows. It's not write once, run everywhere. The old Java mantra that Java and the JVM never managed to live up to. I'm not saying it's that, but you've certainly got all the tools available to make your scripts available to as many people as possible. So why aren't people already doing this? Well, the reason we use shell scripts for these little throwaway utilities is because it's so easy to write, so quick to get done. And although Go is many things, it doesn't have everything you need to quickly bolt these things together. What's missing? Right, 3 things that are missing. First of all, string expansion. UNIX shell scripts manipulate text, and we're going to talk about this a lot more in a moment. It's what makes them so quick to write. You build little building blocks that output a piece of text, and then the next part of your shell script consumes that and manipulates it. And as standard, Golang doesn't give you any of that. We've mentioned that shell scripts have dependencies. They're calling out to the rich ecosystem that Unix operating systems enjoy. And they also, and Bash shell in particular, already has a lot of built-in utilities as well, and I imagine other shells do as well. And again, these are things that there are no direct equivalent, in the Golang library, standard library. And the other thing about shell scripts is they're actually a big text pipeline. Text flows in and flows out and gets manipulated along the way. That's what allows us to take all these little building blocks and quickly drop them together. So pipelines is the third thing we're missing. So what are we going to do about these three things? That's where Scriptish comes in. First of all, it's open source. So it's under the BSD license, so you can use it any way you want, pretty much. And it's specifically designed for porting shell scripts to Go. That QR code and that URL will take you to the repository on GitHub where you'll find the current version of the library. It comes with a comprehensive README and should have everything you need to get started. Now, to help you get started, I want to explain the concepts that Scriptish is built on. Here's an example. All it does is work out how many files of Go source code are in a particular folder, and it writes that output to a file on disk. Now, taken as a whole, this is a pipeline of commands. So that's our first concept. In Scriptish, we create and execute pipelines. And the first thing we need to put into the pipeline is some data. And we call that a source. In our example shell script here, our source is a listing of the files, all the files in a particular folder. That's our source. So sources, they write data into your pipeline. They go and get data from the outside world and put it into your pipeline. That's all they do. So every Scriptish pipeline needs a source. Once data's in the pipeline, we need to do something to it. We need to manipulate it. And we call these filters. Technically, it's filters and transformations. If you see the example on the screen here, the grep command is filtering out every file that isn't a Golang source code file. And then the wc-l command is transforming that data into a count, to a number. It's transferring the list of files into the number of files. But collectively we call these filters because they take data in and they write data back out to the pipeline. So that's what filters are. They go inside the pipeline and they continue the work of the pipeline. So they're taking the data that the source has written, they're manipulating it, and they're putting it back in the pipeline. Now clearly we need to get the data out of the pipeline. And one way to do that is called a sync. And that's when we send the data out of the pipeline to somewhere else. In this example, what we're doing is we're writing that data out to a file called count.txt. But that's what syncs do. They take the data out of the pipeline, normally to disk or to your processor's standard out. So that's the anatomy of a Scriptish pipeline. And it's based on the existing concepts we already use when we write shell scripts. There are sources, which create data. There are filters, which manipulate the data. And there are syncs, which output the data. That's the basic idea. Now, we don't always want to send the output of a pipeline to standard out or to a file on disk. Sometimes we want to get that into a variable, into a Golang variable, so we can do something with it. So if we go back to our UNIX example, in a shell script, you'd wrap it like this. So instead of the count going out to a file called count.txt, instead it gets captured and assigned to the variable count. So we can say, well, what this is a capture method. And so I've introduced the same in Scriptish. There are capture methods available to get data from the Go pipeline back into your code. So if we take our pipeline, we remove the sync, and instead we call capture methods to pull whatever data is at the end of the pipeline waiting to be sunk. Now, that's it. Those are the basic concepts of Scriptish. There is more available. They're all documented in the project's README file. It's the best place to go to see what's available. And once again, there's that QR code, and there's the URL of the project Git repo. But what does this look like in reality? Let's have a look at some actual code. Now, the code I'm about to show you is up on our Git repo. It's in the examples folder. That's the URL for it. And again, that QR code should take you straight there. And this is what the code itself looks like. So very quickly, here on the left-hand side, well, first of all, I'm using Visual Studio Code to demonstrate this. On the left-hand side is my file explorer. And I'm in the examples Git current branch, exactly where I said we would be in the slides. And in here there's a file, main.go, which I've got open here. So let me just make that the main thing. Right. There's some bump at the top. I appreciate scrolling fast means it's very hard to see. I'm going to start from the main function. It's the main entry point for this code. And what have we got here? So first of all, the highlighted lines here, all they do is enable tracing. If you've ever had to debug a shell script and you're wondering why it wasn't working, you'll be familiar with using the -x option on shell scripts to enable tracing. It's so fundamental for writing these type of utilities that I've built in tracing support into Scriptish. It's very easy. You just need those 3 lines of code to enable it. So I'm just to explain what this code does. The purpose of this code is just to print out as what the current Git branch is. So in order to do that, the first thing we need to do is make sure we actually have Git somewhere that we can execute it. And to do that, we are actually calling a Scriptish pipeline called find Git binary. We'll show you what that looks like in a moment. But as you can see, as far as the Go code is concerned, it's just a function call. It's just a regular function call that returns data and a possible error. And you can see here how simple the error handling is. If I highlight these lines, yeah. If there's any error, we just assume that Git's missing from your path for now. That could be made more sophisticated, but it's about on the par with a shell script, so it's probably good enough, in all honesty. Now, if we scroll down here, this is the main meat of it. I've got a second pipeline written in Scriptish that works out what the current branch is. And again, we return the branch name and an error. And if there is an error, this time, the error we're getting back actually means something. It's actually a proper error. So we print its output and we exit with a status to say something went wrong. And if everything worked, we just print out the branch name. So that's the main function, and we haven't looked at any Scriptish yet. But once you've done a little bit of Go and you're a little bit practiced with it, you can knock this kind of thing up really quickly. Really quick to do. And you can see here that we've got some robustness in by making sure we've got a Git binary that we can use. So what is Scriptish doing? So let's go here to our Git, find Git binary. Let me highlight the lines we're looking at. All right. So all we're doing is we've created a pipeline from using the Scriptish package, which has one command in it, one operation if you like, which calls which to find out Git. Let me switch to a terminal. Here we go. So in a shell script, you would literally do which Git in order to find out where Git was installed. And if something didn't exist, you would get empty text back. If I go back to the code, that's exactly the same behavior we have here. And then we're using a capture method to get that result. We've built our pipeline, so we execute it. And then after executing it, we call the capture method to get the answers out. And that may be empty. Now you'll notice, this is very important, we're returning a string and a possibly empty error, which is standard Golang programming approach. So that means all of our capture methods, like trimmed string and all the other ones that exist in Scriptish, they do that for you. They return both a result and a possibly empty error. So you don't have to worry about pulling it apart yourself if you don't want to. So that's our first pipeline. Now let's look at how we get the current branch. Highlighted the lines here. Line 73 to line 90. Now the first thing to say about this is modern versions of Git can do this for you in a single line of code. But I've written this because I'm busy porting some older shell scripts that talk to older versions of Git. And this is how we used to have to do it. So that's why there's so many steps. So what are we doing here? So first of all, we've got an input, and that's the path to our Git binary. So we create our pipeline, and in it, the first thing we do is we want to run git branch -- no color. Line 75 here. And let me show you what that will do. It returns some output that's really designed to be human readable, not machine readable. It produces a list of the branches that exist in the local Git repository, and there's a star in front of the current branch, which in our case is develop. So what we would do in a shell script is we would grep for that branch. We would grep again to filter out any error messages that may have occurred. And then we would use the cut command to get the particular field we want. Or you would use awk. So what we're talking about is this. Git branch -- no color. Grep to get the star. Grep again to filter out the error messages that may happen, and then we would cut. And it produces an output of develop. So that's how we'd write that in shell script, and that's actually taken directly from the Git flow extension for Git that I maintain. And in Scriptish, it's exactly the same steps. So we've built our pipeline, and then we execute it. Now this time, once we've executed it, we want to see if there's an error at all, because we want to add some more robustness to it on top. And that's what these lines here do, lines 83 to 86. If there's an error, we assume it's because we're not in a Git repo, so we return an error previously defined about that. So we add a little bit of robustness in. And more importantly, we start to standardize the error reporting in the code, so we can start to make this a building block that we can do elsewhere. And if there's no error, we can just grab this trim string and return it. So what we're doing here is, rather than having a reusable pipeline, we create the pipeline every time the function's called. And it's the function that's reusable because we've added this extra error handling into it. And that's a good way to go if you want to start building tools that share a common library. This pattern is the way to go with it. So let's go back to our terminal. Let's go into our examples folder. We'll compile it. Okay, so that's built it. And we now have git current branch there. And if we run it on its own, it tells us we're in develop branch. Check out the master branch. Run it again. You can see, let me just highlight to make sure it's all. You can see it's told us that we're now in the master branch. Let's go back to develop. Right. Now I mentioned tracing. So git. Why can I not do that? Oh, that's interesting. My binary has disappeared. I'm not sure why that's the case. I mentioned tracing, and we've got this -x switch that switches on tracing. So I'm going to do that. And the tracing output's designed to look very similar to what a shell script would look like. So you can see all the commands we're executing with all their parameters. And you can see everything we've written to the pipeline as well. So that's what we've been asked to. That's what's been called. This is Scriptish confirming what it's doing. And here we can see that the string user bin git has been written to standard out of our pipeline. Here we've got a similar thing. We're running git with branch and the no color flag, and the results have been written to standard out, develop and master. And you can see we've got the star as well. And we've got our grep. As a result of that, our pipeline now just contains develop. And we're looking for our no branch, our error. Let me just highlight that for you. That doesn't change the pipeline in effect because there's nothing in there that says no branch. So there's no text to filter out. Then we've got our cut. And it makes sure the pipeline only contains develop. So it gives you the tools needed to debug your utilities quickly and easy without having to run a debugger. And that's important because if you're giving binaries to other people, they may not have a Go dev environment to run a debugger in. So your tools need to be self-contained. They need to be able to debug themselves in that respect. So that's Scriptish. And if it looks simple, if it looks really, really simple, like there's just not much to it at all, that's deliberate. It's a point I made in the workshop and I want to re-emphasize today on this video. Unix shell scripts, we use them because they are quick to write, almost disposable. And there's no point having tools to do that in Golang unless they recreate that same feeling of, oh, we'll just throw something together and it's done. That's the whole point of this. We're not looking to make rich, detailed command line utilities. We're looking to make our shell scripts portable. And Scriptish gives us that. Alright then. So that's Scriptish. I hope you enjoyed this talk. If you did, please hit that thumbs up button and please check out the other videos on my YouTube channel. And this QR code will take you to a list of all the playlists we've got. Some of our talks are broken up into multiple videos for ease of use and ease of editing at the time. So we put them together in playlists for you to watch. And finally, if you've got any questions, do reach out to me and I'll do my best to answer them. Thank you very much.